right, in this module, we're going to look at isothermal transformation diagrams, particularly in the steel system, building on what we talked about in the previous modules on Avrami curves. All right, so we can build these time temperature diagrams from the Avrami curves we talked about last time. And so the time temperature basically gives us something of a not quite a phase diagram, but it gives us a diagram of time and temperature that lets us determine what microconstituents we'll have under those conditions. So we're going to look at the iron carbide system with the alloy composition of 0.76 weight percent carbon, which you'll remember is the eutectoid. And here we're specifically looking at a transformation temperature of 675. So we see we can construct a Avrami curve at 675 where we have y, or the percent that's transformed, on the y-axis. So go in here in percent, so it's 0 to 100, and then time in log seconds on the x-axis. And we see it forms that classic S-shaped curve where we have an initial nucleation, and then it ramps up to the fastest rate in the middle, and then it slows down as more and more is consumed later. And so we can get from this, at a given temperature, how long it takes to start the reaction, 50% of the reaction, and 100% of the reaction. And we can transfer that to this the time and temperature graph that we see here. So ignore what's here for a second, and let's just go over what this is. So on the bottom is on the bottom is time in log again. And then here on the y-axis, instead of the amount transformed, we're looking at temperature. And so here at 675, we want to transfer the data from the Avrami curve. And so you see that we're going to have an initial point here on the green curve that means we have 0% perlite, because this is austenite to perlite. And then we're going to have a 50% curve, which is in the dashed. And then we're going to have 100%, which is the red. So if you kind of follow these points down, so if you translate this point as kind of the initiation of that reaction to here, you get the initial point, and then you get the 50% here to the dashed line, and then you've got the 100% to this final line, right? So basically, this is how we're preparing this time temperature diagram, or isothermal transformation, is by running an Avrami curve at each temperature that we're interested in, and then transferring those points down. So we have 0, 50, and 100% transformed austenite to perlite as the transformation. And so we could do this at other temperatures and get more points to fill out these green, dashed, and red curves that we see down here. So that's what we're seeing. So this is what we call the isothermal transformation diagram, sometimes TTT for time temperature transformation. But again, this gives us austenite to perlite for this. So again, it's only valid for this composition, and it begins at temperatures under 727, right? Over 727 is where we have austenite. So you see kind of a solid line with austenite above it. And then here, you'll notice below 727, it says austenite is unstable here, right? Because it's unstable, but it hasn't transformed yet. And so it does take some amount of time to transform. And we see that at 675, the temperature we've been talking about, it takes a bit of time for it to start, about 10 to the 2 seconds, and then roughly 10 to the 3 or so seconds to complete the reaction. But we see that as we decrease the temperature, so now let's look at 625. So at 625, you'll notice it happens a lot faster. So it starts in a little over 1 second and finishes at around 10 seconds. So it's much faster as we decrease the temperature. So we have initial austenite before it's transformed. and then it starts to form perlite here past the green point. The arrow's off a little bit. And then again, this one's off as well. Sorry, but this is where we have this should be after the red line here. So that kind of gives us the microstructure that we've been expecting. And again, all of these curves were basically put together by multiple different temperatures and running that isothermal experiment where we look at the Avrami curve for that temperature. And so we've put together these curves. So this is for the austenite to perlite. And you'll notice that it kind of stops here a little over 500. So we're going to talk about that in a second. All right, so that was one composition. We can make similar transformation diagrams for other steel compositions. So if we consider the 1.13 weight percent, so now 1.13 weight percent, we're over here. So whereas the 0.76 was the eutectoid, here we're hyper eutectoid. So we should get pro eutectoid cementite, Fe3C. And so in this diagram, you see similar green dashed and red curves for the austenite to perlite. That's what the A and P mean. Austenite is A, P is for perlite. But you also see another region here, the orange curve, and that represents austenite going to austenite plus cementite. So this is basically the pro-eutectoid region of the diagram. And you see here that we don't sort of put any percents here. It's just that we have it or we don't. And so that's what we see with this composition. So there can be variations of these diagrams depending on where they're at. If we had a diagram over here for the hypoeutectoid, then we would expect to see ferrite instead of cementite. So because it's a hypereutectoid, we see proeutectoid cementite. All right, but like I said, these only went up to 500 degrees or so. Below that temperature, below about 550, instead of perlite, we actually start to see something else that we call bainite. And so this is also a mixture of alpha or ferrite and cementite, Fe3C. However, it doesn't have that same appearance as perlite. Instead, it forms these very small needles. So this is a very zoomed in picture from electron microscopy. So this is just showing a portion of one of these bainite crystals, or bainite particles. And you see that within this very small, 1 or 2 microns across, you see that there's regions of ferrite and cementite within this very small needle. So the dimensions are much smaller than perlite. So that's what bainite is. It's just these elongated particles in a ferrite matrix. So they do look kind of needle-like in appearance. And they are kind of controlled by diffusion. If we lower the temperature, diffusion has to happen on very small length scales. Just like we saw at the lower temperatures of perlite, we formed fine perlite because of the diffusion distances at the lower temperatures, as opposed to coarse perlite at the higher temperatures up here. So bainite basically forms down here, and we see that it follows the reverse trend. At the higher temperatures, bainite reaction is very quick, so it happens within a matter of seconds, and then lower temperatures, it's slower. And this is because, as you can imagine, it's now becoming diffusion limited at those low temperatures, and so the rate slows back down. So that's kind of why you see that. And overall, if you look at this curve, if you combine the perlite and the bainite regions, it has that C-shape appearance where the rate is fastest in the intermediate temperatures and then slow at high temperatures and low temperatures. So up here above 550, we have perlite, and then down here we would have bainite. And I do want to mention one other microstructure of these eutectoid steels is that we know that we get that lamellar layered structure from perlite, and we know that we get a similar type of structure where we have layers or grains of Fe3C and ferrite. However, those have relatively high surface areas for the particles of ferrite, or sorry, for Fe3C. If we hold these steels at long enough times, at high enough temperatures, that high surface area is unfavorable. And so these particles will transform into what we call spheroidite. And as the name might imply, it's referring to spherical particles. And we're specifically talking about roughly spherical particles of cementite in kind of a matrix of the lighter phase, which is ferrite. So basically, spheroidite, because we have a sphere, is the lowest amount of interfacial energy between those two species, right? So if we compare that to perlite or bainite or any other species, this gives us the lowest interfacial energy. So this happens to steels when you hold them at really high temperatures for a long enough time to kind of minimize that grain, that boundary interface that we see. All right, and the last microstructure that I want to talk about for steels is a non-equilibrium phase. So this is something that we haven't seen on the phase diagram because it's non-equilibrium. And what it is it's a non-equilibrium phase, and it's formed by quenching. So in the past, we've talked about how we can kind of freeze in the liquid state by quenching a polymer or by quenching a ceramic to form a glass. This is similar. However, we're quenching in a non-equilibrium crystalline state. So that's what's kind of happening here. And so we start with austenite, gamma iron, which has an FCC structure. And we know from the phase diagram that this contains a lot of carbon. All of the carbon is basically soluble up to 2.8%. However, we know ferrite has a very low solubility of carbon. It's actually 0.02%, so it's a very small amount. So if you quench this austenite structure, it has all this carbon saturated in the structure, and it won't be able to diffuse out the carbon to form Fe3C and ferrite, or the BCC structure. So what happens is it becomes this kind of metastable non-equilibrium phase known as Martensite, which has a very similar structure to the FCC. It's actually BCT, so body-centered tetragonal, and it looks like this. So here's the iron atoms on the corners, and then here on the edges we see potential sites for carbon. And so this is kind of the Martensite structure, and because it's done by quenching, it's in this lowest region. So we basically have to cool very rapidly to avoid forming bainite or perlite. And so this is a very rapid transformation, and we actually call this a diffusionless transformation because if diffusion occurred, it would form ferrite and ferrite and cementite. So this is actually a dimensionless transformation, and that's why we kind of give them horizontal lines here, because it's not dependent on time, it's only dependent on temperature. So as long as we cool down below these temperatures, we see that we form this microconstituent if we haven't formed anything else. So as long as we have austenite at these temperatures, we will form we will form Martensite at these temperatures. So it's a rapid cooling of this material. So let's kind of go over some of the kind of different scenarios here that we can have for these different phase transformations. So we're always starting with austenite at the highest temperature, which has the FCC structure. If we slow cool it, we get ferrite and cementite in some form. If we quench it, we get Martensite, which is the BCT structure, as opposed to the BCC or the FCC. And so Martensite is a single phase. It's not an equilibrium phase, but it is a phase because it has a unique crystal structure and properties. And again, it's body-centered tetragonal. And it's that diffusionless transformation. And it actually forms into that if they have a low amount of carbon. So BCT is also a system that has few slip planes, and that makes it hard and brittle, as opposed to some of the other ones like FCC or BCC, which have more slip planes and therefore are more ductile. And if we take that martensite, which is non-equilibrium, if we heat it back up, allowing for diffusion to occur, we'll undergo a process called tempering, which will get it back to the equilibrium ferrite plus cementite in some way or another. So there's a whole series of materials called tempered martensite, and that's basically taking this metastable phase, non-equilibrium, and heating it back up to getting some version of this configuration here. Okay, so far we've just talked about iron and carbon. However, as you might be aware, steels have a lot of other alloying elements in them. And so here we're going to kind of talk about what that does to them. So this is a TTT or isothermal transformation diagram of another steel composition which has other elements. And so things like chromium, nickel, molybdenum, silicon, and manganese, what they do is they slow down the equilibrium reaction of gamma to alpha plus Fe3C, right? So perlite or bainite reactions. And what that does is you can see over here, as opposed to the eutectoid one that we've looked at before, where the reactions happen within a matter of seconds, you can see the perlite reaction here is now at 10 to the 3, 10 to the 4 seconds, and then bainite here is at 10 or 10 to the 2 seconds. So they've actually slowed those reactions down. And what that does is it allows for those reactions to be slowed down and to more easily form this hard, strong martensite structure, even though it is more brittle. So a lot of times alloying elements will be there to increase the prevalence of martensite, make it easier to form martensite because we can avoid forming these because we've slowed down those reaction rates. And so that's what elements like this will do to a reaction. So you're going to get a different transformation diagram here because of these elements affecting the reaction rates of the different phase transformations that we've just seen.